I could multiply 7 by itself 5 times and then divide by 3 and see what the remainder is. But I could also make the following observation. So what is 7 congruent to modulo 3? So 7 goes in twice with a remainder of 1, correct? So this is congruent to 1. So if I want to find 7 times 7, that's congruent to 1 times 1. And 1 times 1 is just 1 modulo anything. And 7 times 7 times 7 times 7 times 7 will be 1 times 1 times 1 times 1 times 1, which is just 1. So without really doing a whole lot of work other than dividing 7 by 3, I know that this is congruent to 1 modulo 3. And, if you're on a Linux system, I can do 7 to the 5th. And if I subtract 1, and divide by 3, I can see that I get an even integer, exact integer. So this is a very simple way to do exponentiation, and by the same token, I know that 7 raised to the 1005th will be congruent to 1 modulo 3. Because 7 to the 1005th is just 1 to the 1005th. So there's 7 to the 1005th. There's 7 to the 1005th minus 1. And if I divide by 3, I get a perfect integer. So that's one trick we can use, right? We can reduce this modulo, whatever our number of interest is, and then do our exponentiation on that. Now, that doesn't always work out that nicely. If it happens to be congruent to 1, you're not going to have to do any work because 1 raised to things is just 1. I had some printing mishaps, so I'm reusing scrap paper today. But suppose we wanted to do 8 to the 5th is congruent to what modulo 3? Well, 8 is congruent to what?
2.
8 is congruent to 2, thank you. So 8 squared is congruent to 2 squared, which is 4, which is congruent to 1. 8 cubed will be congruent to 8 squared times 8. Well, 8 squared is 1 and 8 is 2, so that's 1 times 2, which is 2. 8 to the 4th will be congruent to 8 cubed times 8, which is 4, which is congruent to 1, and 8 to the 5th will be congruent to 8 to the 4th times 8, which will be 2. So you had to do a little more work there. But we could also have done this. 8 is congruent to 2, which is also congruent to minus 1, right? 8 is 1 less than a multiple of 3, namely 9. And so 8 to the 5th is congruent to minus 1 to the 5th, which is just minus 1, which is the same as 2. So sometimes we get lucky. Sometimes we have a number that's congruent to something simple, and we can do multiplication or exponentiation without having to do a whole lot of work. But that's just if we happen to be lucky. So what we want to do is find a general algorithm for doing large exponentiation. And the algorithm we're going to start with is just called modular exponentiation. And I got to warn you, if you go online and ask how do I do this using modular exponentiation, you'll find lots of answers. I want you to know the algorithm that we're about to go over right now. And if I ask you to use modular exponentiation to solve a problem and you use a different algorithm, you don't get credit for it. I want you to know this algorithm because this is an algorithm we can teach a computer and it's extremely efficient. And modular exponentiation is sometimes considered a general term. And so there's other algorithms you can use to accomplish this, but they don't count. So this is the algorithm that we're going to mean when we talk about modular exponentiation. So let's do an example. Um, so example, find 3 to the 17th modulo 7. Now we know we can take 3 and we can multiply by itself 17 times and keep reducing mod 7. But that's going to take us, 16 or 17 operations. We can do a lot better.
Oh no.
So here's how this algorithm works. Start with 3 to the first, and 3 to the first is just 3, mod 7. I'm not going to keep writing mod 7. So everything we do for this problem is mod 7. So just keep that in mind. Okay, from 3 to the first, go to 3 squared. And this is the square of 3, which is 9. And what is 9 modulo 7?
Two mod 7. So,
Sorry, say again?
uh, 2 mod 7. So
Yes,
sorry,
congruent.
just
Yep,
mod
perfect.
7.
Thank you. All right, so 3 squared is congruent to 2. We're not going to do 3 cubed. We're going to jump up to 3 to the fourth. And 3 to the fourth is the square of 3 squared. And 3 squared was congruent to 2. So 3 squared squared will be congruent to 2 squared, which is just 4. And we're not going to do 3 to the fifth, sixth, or seventh. We're going to square both sides. We're going to say 3 to the eighth, and this is the square of 3 to the fourth. And we already found 3 to the fourth was congruent to 4. So 3 to the fourth squared is congruent to 4 squared, which is 16. And 16 is 2 more than 14. And then we're going to skip 3 to the 9th, 10th, 11th, 12th, 13th, 14th, and 15th. We're going to jump all the way up to 3 to the 16th. And that's the square of 3 to the 8th. And 3 to the 8th is congruent to 2, so this is 2 squared, which is 4. All right, that's the first part of modular exponentiation. Start with 3 to the first and keep squaring. Find 3 squared to the fourth, to the 8th, to the 16th. And we didn't have to do 16 operations to get this. We did basically 1, 2, 3, 4 operations. So now we take our exponent that we're interested in, and we write that as a sum of powers of 2. So 17 is equal to 16 plus 1. And if you're not sure what the powers of 2 are that add up to 17, just write 17 in binary. 17 looks like this, right? 1, 0, 0, 0, 1, base 2, which means 2 to the 0 plus 2 to the 4. So 1 plus 16. So whatever way you have to do it, figure out how to write your exponent as a sum of powers of 2. And now we use something called the law of exponents, which says 2 to the 17th is 2 to the 16th plus 1. This is equal to 2 to the 16th times 2 to the first. So the law of exponents says if you have things added together in your exponent, you can break those out and multiply the pieces. So that's the second step. And then the third step is to put those together. So 2 to the 17th equals 2 to the 16th times 2 to the first. This will be congruent to, sorry, these should all be threes for us. I mean, they work regardless of the exponent, but we're trying to find 3 to the 17th. So 3 to the 17th is 3 to the 16th times 3 to the first, which is congruent to 3 to the 16th is congruent to 4, and 3 to the first is congruent to 1, and 4 times 1 is just congruent to 4. So 3 to the 17th should be congruent to 4 modulo 3. Except I didn't write 4. 3 to the first is congruent to 3. My bad. 4 times 3 is congruent to 12. And what is 12 modulo 7? That's congruent to 5. Really easy to make silly mistakes arithmetically. So there's a lesson there, right? If you do this and I saw you write out, 4 times 1, but you already told me that this was 3 to the first and you told me 3 to the first was 3, I'm going to look at that. I'm going to say, oh, you copied the number down wrong. Probably not going to lose any points. But if you do all this in your head and you just write down the final answer and the final answer is wrong, you don't get credit. So show your work, right? Because it's really easy to, do silly mistakes like I just did a couple of times. So 3 to the 17th minus 5 is this. And if we divide by 7, we get a whole number. So 3 to the 17th is 5 more than this multiple of 7. But if we wanted to find, 3 raised to the millionth modulo something, instead of doing a million multiplications, we'd have to do 20. Because if we double 20 times, we get up to a million. So this is a huge time saver. All right, so let me have you work on one of those. Um, let's do let's do 6 to the 50th modulo 11. So take a few minutes and use modular arithmetic. Try to come up with this answer modulo 11. And when you get an answer, send me a direct message in chat. Or if you're stuck and you're not sure how to go, send me a message and I'll give you some pointers. And if enough people get stuck, we'll just talk about it in the class. So let's take about 5 minutes and go ahead and work on that. I'll give you a count. All right, had answers from two people. Where are the rest of you? Are you making progress? All right, answers from three people. So yeah, 6 to the 1st is just 1. 6 to the 1st is not 1. Oh, messed up, but I got the right answer. All right, we'll just do that ourselves. Um, so 6 to the 1st is 6. 6 squared is 36. And 11 is kind of nice, right? Because 11, 22, 33, 44, it's easy to pull up multiples of 11. So the closest multiple is 33. This has a remainder of 3. 6 to the 4th will be 3 squared, which is 9. 6 to the 8th will be 9 squared, which is 81, which is 4 more than 77. So that's 4. And then 6 to the 16th will be 4 squared, which is 16, which is 5 more than 11. So that gives us a 5. And then 6 to the 50th, well, 50 is 48 plus 2. 48 is 32 plus 16. So it's 6 to the 32 plus 16 plus 2. We gotta go one more. 6 to the 32nd is 5 squared, which is 25, which is 3 more than 22. So this is congruent to 3. 50, if you write it in binary, looks like that. So it's 2 to the 1st, 2 to the 4th, 2 to the 5th. That's 2 plus 16 plus 32. So 6 to the 50th is 6 to this exponent. And then law of exponents says this is 6 to the 32 times 6 to the 16th times 6 squared. 6 to the 32nd is 3. 6 to the 16th is 5. And 6 to the 2nd is 3. So 3 times 5 is 15, times 3 is 45, and that's 1 more than 44, so that's congruent to 1 modulo 11. And then if you want to check, uh, 6 to the 50th looks like that. 6 to the 50th minus 1 looks like that. And if you divide by 11, it goes in that many times, which is a even exact integer. So that's modular exponentiation. You can also make your life even easier if you don't mind negatives, because, for example, 9 is actually congruent to -2, and then -2 squared gets me to 4. So if I'm working mod 11, I never really have to work with numbers bigger than 5, right? I could have, instead of working with 6, if I didn't want to square 6, I could have said this was congruent to -5, and then 6 squared would be congruent to 25, which is 3 more than 22. So this really lets you work with large numbers without having to actually interact with large numbers. It lets you do calculations involving large numbers while sticking with relatively small numbers. Um, and again, for a computer trying to do something like this, instead of doing 50 calculations, it does, 5 or 6 calculations. Big difference if you wanted to raise 6 to the 1,000,000,000th power, it would take you 30 calculations. because 2 to the 30th gets you to around 1 billion. If you wanted to raise it to the trillionth power, it would take you 40 calculations. So you want to do something with 40 multiplications or a trillion multiplications, probably 40. This is a really powerful algorithm. All right, so questions about that? All right, so let's talk more about primes. So we defined these last time, right? A prime is a number that's only divisible by itself in one. And so numbers like 2, 3, 17, 101 are prime. Numbers like 25, 36, 9 are not prime because they're divisible by others. Oh, cool. Excellent. Yeah, I messed up when I did my calculation. While everyone was doing theirs, I did 6 to the first equals first, which is not true, but I stumbled across the right answer anyway. Yeah, these things happen sometimes. All right, so primes, numbers not divisible by anything except themselves in one. 6 squared congruent to 1. Okay. That's not as bad as 6 to the first congruent to 1, which I did. Um, so let me give you a theorem here. It's called the fundamental theorem of arithmetic. Every discipline seems to have a fundamental theorem, even arithmetic. So what is this fundamental theorem? It basically says that, if you have a number that's not prime, you can factor it into a product of primes. So every positive integer bigger than 1 can be written uniquely as a product of primes. And there's a little lawyer's asterisk on this word uniquely, which means there's a footnote or a clarification to that. What do we mean by uniquely? Well, first of all, if I take the number 7, I'm just going to write it as 7. I'm going to call that a product of primes. Usually a product has 2 or more things, but we can just think of this as a product of one number, right? It's just the number 7. So we're going to count that as a product. The unique business, if I take the number 10, I can write that as 2 times 5. That's a product of primes. I could also write it as 5 times 2. That's also a product of primes, but we're not going to consider these to be different products. So when we say uniquely as a product of primes, we mean up to rearranging the order of the numbers. And we're not going to count different rearrangements as different products. So the fundamental theorem says that if you have a number that's not prime, you can write it as a product of primes. And there's a unique way to do that other than, the obvious rearrangement of numbers. And so 1001 is 7 times 11 times 13. And there's no other way to factor 1001. It's not like it's 17 times something else, right? If we write it as a product of primes, this is the only way to do it, other than, 11 times 7 times 13 or 13 times 7 times 11 and so on. Now I can write 1001 as different products. I could write it as 77 times 13, right? But 77 is not prime. So the fundamental theorem says you can write it uniquely as a product of primes. And it's a really powerful theorem, and it turns out it's not true for all sets of numbers. It's true for integers. But for example, if we work with integers with some other things added in, this fundamental theorem breaks down. And that was surprising to people when they discovered it. But for integers, this always holds. All right, so how do we test for primes? So someone gives you a number and wants you to tell them, is this number prime or not? How would you do it? What are some of your options?
Uh, I would say you check the number of factors it has. So if it has like one and it's off, then it's a prime number. That's
Okay,
my like
good.
my yeah.
Okay, so how would you find out what the factors are?
I'm imagining since like prime numbers already have like two factors. That's like a known thing. So you're basically proving that this number has only two factors. So one and it's off. If it has any more other factor, then it's not a prime number.
Okay, so we would look for other factors, and if it's only one in itself, then it's prime. So how do we look for factors? Someone comes up to you on the bus and they say, I'll give you $100 if you tell me if this number is prime or not. What are you going to do? How are you going to look for factors? Is it possible? There we go. Divide by numbers less than the number. Sure. You want to know if the number 57 is prime or not? Start dividing by numbers. Okay, well, we know it's divisible by 1. We don't care about that. Is it divisible by 2? Well, no, I'm going to get 28.5, so that's no good. Is it divisible by 3? Well, it goes in 1, 9, 19, 27. Yeah, it goes in 19 times, so it's divisible by 3. It's not prime. If I try that with 59, divide by 2, I'm going to get, a 0.5. If I divide by 3, I'm going to get 19.666. If I divide by 4, well, it's not going to go in because it's not an even number, and so on. You keep doing this, and it's not divisible by anything up to and including 58. That's going to turn out to be prime. So this is called trial division. Oh, this is called out of ink. So trial division is just try dividing. Divide by 2, divide by 3, divide by 4, and so on. If you don't find a factor, then it's prime. If you find a factor, you know right away it's not prime. So how many numbers do I have to try dividing by? Suppose I'm working with a number 19,937 and I want to know if it's prime or not. Certainly if I try dividing by each of these and none of them divide it, right? So that would be all the numbers up to itself minus 1. Someone said up to its square root, right? So this is a big time saver. I only have to go up to the square root of the number. So if I'm testing like the number 101, I only have to try 2, 3, 4, 5, 6, 7, 8, 9, and 10. Because if I divide by a number bigger than the square root, I'm going to get something less than the square root. We actually proved this last week in our discussion of proofs. If the product of two things was n, then at least one of them was less than or equal to the square root. So if we have two numbers that multiply to 101, one of those numbers has got to be less than or equal to its square root. So we don't have to go all the way up to 100 or 19,936. We only have to go up to the square root. And that's a big time savings. If you're testing a number around 1,000,000, you only have to go up to 1,000 instead of 1,000,000. There's also other things we can do. We know that if the number is even and it's bigger than 2, it's not prime. If the number is odd, we don't have to check any of these even numbers. Because if it's divisible by 10, it's divisible by 2, because 10 is 2 times 5, right? So we really only need to check the number 2, and then we need to check odd numbers up to and including its square root. If it ends in 5, other than 5, we know it's not a prime number, because any number that ends with 5 is a multiple of 5. And we talked about last time how to tell if something's divisible by 3. Just add up the digits. And if the sum of the digits is a multiple of 3, the whole number is a multiple of 3. So there's lots of little tricks we can use. And so the Greeks had a method for actually generating primes. It's got a cool name. It's called the sieve of Eratosthenes. And a sieve is, like if you're panning for gold, like in a Bugs Bunny cartoon, it's a thing that has like a mesh bottom to it, and you scoop up water in it and you shake it, and the water falls through the openings in the grate, and the sand falls through. But things that are bigger than that, like little nuggets of gold, will get stuck. So the sieve of Eratosthenes is like panning for prime numbers. And it works like this. You write down a bunch of numbers. I'm only going to go up to like, I don't know how far. I'll go up to 50. You had a lot of time if you were an ancient Greek, I imagine. So you could do things like this. All right, so there's our first 50 numbers. And we know one's not a prime, so we're not gonna worry about one. We're gonna start with the number 2. All right, I'm going to circle this number, and then I'm going to cross out every other number after that. So I'm just going to go up by 2s and cross out. Not really doing a lot of thinking, just some really fast counting. All right. The next number on the list that is not circled is guaranteed to be prime. So that would be the number 3. So I'm going to circle that. And then I'm going to cross out every third number. So I'll cross out 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48. The next number that's not crossed out is guaranteed to be prime. That's the number 5. Cross out every fifth number after that. That takes out 10, 15, 20, 25, 30, 35, 40, 45, and 50. And we just keep going. Next number is 7. Cross out every seventh number. 14, 21, 28, 35, 42, 49. Next number that's not crossed out is 11. That's going to be prime. Cross out every 11th number. 22, 33, 44, and there's no 55. Next number is 13. Cross out every 13th number. So 13 is prime. We'll cross out 26 and 39. And then 52 if it was on there. Next number is 17. Cross out the multiples of that, 34. Next number is 19. Cross out multiples of that, which would be 38. 23 multiples of that would be 46. And then 29. And if we look at the first multiple of that, we're bigger than 50. So all the remaining numbers are guaranteed to be prime. So there's 37, and there's 41, and 43, and 47. There's all the prime numbers up to 50. So that's a cool little method. Somewhat limited in its practical application. We wouldn't try to generate 1,000-digit prime numbers like this, but we can find some interesting characteristics of primes by thinking about them from this perspective, perhaps. All right, that's 1 o'clock. Let's go ahead and do a 5-minute break and come back at 1:08, and we'll keep digging into characteristics of prime numbers. So I'll see you back in about 5 minutes. All right, and we're back. So, how many prime numbers are there? Someone said infinite with a question mark. What do you think? So the range of integers is definitely infinite. But is it possible, as numbers get larger, they get more and more possible factors? If you look at the amount of space up to the square root, there's more possible things to consider as potential factors. Um, but you are correct. Theorem, there is no largest prime number. Primes go on forever. And this is a nice example of where a proof by contradiction works really well. So let's prove this. So suppose n equals the largest prime number. Let's assume that the number of primes is not infinite and there is a largest prime number. So let's just call that number n. That's the biggest prime. You get up to 1001. There's no primes bigger than that, say. Okay, let's make a new number. Let b equal the product of all primes. And since there's only a finite number of primes by our assumption, we can take the product of that finite number of primes. We get a really big number called b for big. Well, consider b plus 1. Take the product of all your prime numbers and add 1 to it. That's the number b plus 1. Can that be divisible by any prime number? So let's just number our primes. Let's think of our primes as P1, P2, P3, all the way up to, I don't know, P sub m for maximum, right? B plus 1 is the product of all of those. Plus 1. So b plus 1 is one more than a multiple of p1. It's one more than a multiple of p2. It's one more than a multiple of p3. It's one more than a multiple of every prime. So b plus 1 is not divisible by any prime. Well, by the fundamental theorem of arithmetic, b plus 1 should be expressible as a product of prime numbers. And since we can't write it as a product of any of these known primes, b plus 1 itself must be prime. But the problem is b plus 1 is much bigger than this number n, right? N is this largest prime number, and b plus 1 is this number multiplied by a bunch of other stuff plus one more. B plus 1 is bigger than this largest prime. How can it be prime? That's a contradiction. So the conclusion we're forced to is we cannot find a number n, which is the largest prime number. So there must be no largest prime. So the Greeks knew this, right? This was how they figured out that there were an infinite number of primes. And it's a nice, proof by contradiction. A direct proof of this, much harder. But showing that, something absurd happens if the opposite is true, forces you to conclude that the opposite is not true. So we know there's an infinite number of primes. And this leads us to wonder what the nature of this infinite set of primes is. Yeah, it'd be a little tricky to use the sieve for that. um, so we can question the nature of these prime numbers. Um, and so here's an interesting idea. Powers of two. So 2 squared is 4. If you subtract 1, you get 3. That's a prime number. 2 cubed is 8. You subtract 1, you get 7. That's a prime number. 2 to the 4th is 16 minus 1 is 15. That's not prime. 2 to the 5th is 32 minus 1 is 31. That's a prime number. 2 to the 6th is 64 minus 1 is 63. Not prime. 2 to the 7th is 128 minus 1 is 127. That is prime. Anybody seeing a pattern in here?
2 to the power of a prime number minus 1 is a prime number.
Yeah, if this exponent is prime, 2, 3, 5, 7, when we raise 2 to that and subtract 1, we seem to be getting prime numbers. 2 to the 9th minus 1 is 511. And 511 is 7 times 73, so that's not prime. So this seems to hold. And in fact, it does hold a lot of times, but it turns out it's not always the case. What we do know, if we look at 2 to the n minus 1, if n is composite just means not prime, then we know 2 to the n minus 1 is also not prime. If n is prime, we don't know if 2 to the n minus 1 is prime or not. Sometimes it is, a lot of times it is, but not always. So there's a piece of terminology here. If 2 to the n minus 1 is prime, this is called a Mersenne prime. Do I know how to spell that? It's probably got an extra E somewhere. I think there's an extra E there. Mersenne is a mathematician's name. Let me see if I can find you a table here. Otherwise, I'll just go to Wikipedia. I'm just going to Wikipedia. So here's a wiki page with a list of Mersenne primes. So 2 to the 2, 3, 5, 7. 2 to the 11th is actually not prime. 2 to the 11th minus 1. That would be 2047. Should know what this is. 2047 is 23 times 89. So 2 to the 11th minus 1 is 2047. That's the first one that breaks this pattern. That turns out to be a composite number. So you can find tables of which powers of 2 minus 1 give you a prime number. So 2 to the 2, 3, 5, 7, 11 doesn't, 13 does, 17 does, 19 does. 11's an oddball. So these are called Mersenne primes. So this table shows you the value of that number, the number of digits in it, and when and how it was discovered. So these first few, these were known to the Greeks. 2 to the 13th was recorded in the 13th century. So this was, when Europe was coming out of the Dark Ages, but uh, the rest of the world was developing algebra and algebraic manipulations, and were able to do large calculations like this. And so with trial division, they found that, 8,191 was prime. In the late 1500s to the 17th to the 19th, also discovered through trial division. So the Italians are getting in on this now. And, these are 6-digit numbers. So not the end of the world, but, dividing this by every possible factor up to its square root, that's a lot of work. But, got time to kill, I guess you can do it. And then 2 to the 31st, Euler, geometer, mathematician. We'll look at him when we do graph theory at the end of this course. In the 1700s, tackled 2 to the 31st minus 1. It's a 10-digit number and showed this was prime. And it was trial division, but with modular restrictions. So we knew about modular arithmetic at this point. We knew about things that we've talked about, like if a number ends in 5, it's divisible by 5. Using those kinds of ideas, he was able to tackle this 10-digit number and show that this was, in fact, a prime number. Scoot forward a little over a century, 2 to the 61st was the next Mersenne prime. And that was discovered using something called Lucas sequences. So Lucas was a mathematician. There's another mathematician named Lemur, and together there's this thing called the Lucas-Lemur test, which is used today to test for Mersenne primes. So he discovered properties of sequences of numbers that you could generate based on this exponent. And if that sequence had certain properties, you could conclude that this corresponding Mersenne number was prime or not prime. So these next numbers were discovered by different people using Lucas sequences. And so we're in the late 1800s here, early 1900s. And then there's a bit of a dry spell until the 1950s. And the 1950s, we start finding new primes using these Lucas-Lemur tests on SWAC. So SWAC was an early electronic computer, National Bureau of Standards. And so now we got computers in the game. And this was sometimes the way that computers were diagnosed to see if they were working correctly was to test for Mersenne primes, right? Using a Lucas-Lemur test. So we're getting up to numbers with, hundreds of digits. 2 to the 2,203 has 664 digits. And this is the 1950s, right? This is 75 years ago. We were able to determine these numbers were prime. Using SWAC, using BESC, which was another computer, the IBM 7090, which was a monster of a machine, Iliac 360, which was the classic big iron machine. So now we're into the 60s and the 70s, and our exponents are getting much bigger. So 2 to the 19,937 was the largest known prime when I was a kid and I was getting into prime numbers. And Guinness Book of World Records would publish these um, in their yearly paperback. And that just blew my brain that like we could do anything about a number with 6,002 digits. Um, so more big iron, CDC, Control Data Corporation's cyber computer, and then Seymour Cray left CDC and started building his supercomputers. First one being Cray 1. And these were just chowing on larger and larger Mersenne primes. NECSX was another supercomputer, Cray's XMP, Cray XMP 24. So, more and more computational power going into these, and the numbers are getting quite large, right? A number with 65,000 digits, and testing its primality using Lucas Lemur tests. So this is in the mid 80s. And then something changes in 1996. We go from a Cray T94 to the next Mersenne prime being discovered on a Pentium PC, right? A 90 megahertz Pentium PC. Anybody here ever use like a 90 megahertz PC? My first one was 75. Um, it's not that long ago, but it was a big difference. But anyway, how do we go from using these large supercomputers that, the government was running to somebody finding a prime on their 90 megahertz Pentium? And this was something called GIMPs. This was the Great Internet Mersenne Prime Search. And in the mid 90s, people realized that like lots of people had PCs, and a lot of the time those PCs were running screensavers, right? So old monitors, cathode ray tubes, if you kept the same image on the screen, it would burn into the phosphor. So you would change the image over time. And if you walked away from your computer, you didn't want it to just have whatever was on there. So a screensaver would run to change what was being displayed to prevent burn-in. But your CPU is doing nothing except drawing pictures that nobody's even looking at because you're asleep. So some people decided, hey, we could take advantage of all of these idle CPU cycles to do something like search for primes. And so there was this program you could join called GIMPs, and you would download a piece of software, and instead of running a screensaver that showed, flying toasters or colored balls bouncing around, it would run algorithms to check for Mersenne primes. And you would talk to the server, it would send you a number to test, and you would run this Lucas Lemur test. And if it finished and said it's not prime, it would report that back. If it finished and it reported that it was prime, well, you'd be famous for a little bit. Your name would show up on Wikipedia, in 2026, saying you discovered the 35th Mersenne prime, for example. And so the next set of primes all came out of GIMP, right? And this was free cycles. And so this was an early example of crowdsourcing. And crowdsourcing has been used for a lot of things. So SETI, Search for Extraterrestrial Intelligence, had a crowdsourced program called SETI at Home. And SETI, they collect radio signals from space and they analyze them for markers of possible intelligence. And there's, lots of debate about what that means, but there's people who are pretty convinced that if there is intelligent life somewhere and they're using the electromagnetic spectrum to communicate and do work, that there are markers of that we would eventually receive here on Earth. So you could run a SETI at home on your computer, and when your machine was not doing anything that you asked it to do, it would go to a server and pull down samples of signals received by radio telescopes and run this analysis on it. And if it found something interesting, it would report that back, and then more analysis would be done. When COVID came out, there were programs you could download that would use your machine to do things like protein folding to try to find, possible vaccines to interfere with COVID. So this is an idea that's caught on and is still in popular use. But one of the early examples was searching for Mersenne primes. So PCs got more powerful, 200 megahertz, 800 megahertz Athlon. And finally, we got up into the gigahertz in 2003, 2.4 gig, um, 3 gig in 2009. And so at this point, we're not sure that we're finding consecutive Mersenne primes, but these numbers are all guaranteed to be Mersenne primes. Um, and then the largest known one today, which was discovered 15 months ago, I guess, to the 136 millionth, 279,841 minus one. And, we're into GPU land here, because that's where you get your best computation. So this is an interesting journey from, ancient Greeks doing this by hand to very smart mathematicians like Euler doing very clever things, and now we're just kind of brute forcing on, you know, random PCs that people just want to kind of like contribute to the cause. Um, so anyway, that's the deal with Mersenne primes. Um, I don't think we've determined if there's a limit to the number of Mersenne primes, and we have absolutely not found a pattern as to which primes will give you Mersenne primes and which ones won't. Um, there's a lot about prime numbers that we just don't know. And part of why so many people are interested in this is because there's a lot of questions that are easy to understand the question, but for which the answer is very hard to discover. And that's a compelling source of problems. Um, if you look at the distribution of primes, our first few primes are 2, 3, 5, 7. I mean, those are two numbers right next to each other. These differ by 2, these differs by 2. We have to go up by 4 to get to the next one, and then we go up by another 2. Then we have to go up by 4 again, but then just another 2. Um, these numbers are relatively close to each other. They're almost as close as they could be, right? We know 18 can't be prime because it's even. When you get further out, these numbers start to get farther apart, but we still find these so-called twin primes, consecutive numbers, consecutive odd numbers that are prime. So twin primes are numbers n plus 2 that are both prime. And they're very common in the beginning, 3 and 5, 5 and 7, 11 and 13. But as you get to larger and larger numbers, these get rarer and rarer. So question, is there a largest pair of twin primes? And we don't know. We don't have an answer to that. We don't know if they go on forever or if there's some point after which all your primes are separated by at least 4. It's an open question. We do know that in general, though, primes get further and further apart the further out you go. And that makes sense because it's harder and harder to be a prime if you have more potential factors. If you take a number like 19, there's only a few numbers that might divide it, right? 2, 3, 4, 5. Five's too big, right? But if you take a number like a trillion, right, you've got a million possible factors below its square root. So primes tend to thin out as you get larger, but so far, every now and then we find pairs of these numbers that are right next to each other that are both prime. So related to that is the question, how many primes are there below some point? So if you go up to 100, there's, I don't know, maybe 20 prime numbers. If you go up to 1,000, there's not 200 prime numbers. If you go up to 1,000,000, they get even rarer. So if you were to draw a graph like n and the number of primes less than or equal to n, it does something like that. And we know this is going to keep going up. If this got flat at some point, that would mean there's a largest prime, right? There'd be some number after which the number of primes doesn't go up. So we know this is always increasing, and it increases a lot in the beginning, but it increases more slowly over time as n gets bigger. And it's not smooth, of course, right? The number of primes is an integer. So it actually, looks like this and then jumps up. But sometimes, it will jump up twice on two consecutive odd numbers. Those are twin primes. And the study of this is a fascinating area. This gets you into so many bizarre, deep things. If you want a wormhole to lose yourself in, just Google the zeta function. And I mean, you can spend several lifetimes just digging into the zeta function. Um, but let me give you a result that is proven and well understood, um, and fairly bizarre. So let me define a function. Let p of x equal the number of primes less than or equal to x. So as x gets larger and larger and approaches infinity, p of x gets closer and closer to the natural log of x. The log base e, that number 2.71828, gets closer to the natural log of x. And that should feel a little bizarre because logarithms are strange things, right? And e is a weird thing. It's this, base of natural logs, 2.718, etc. And that those things should tie together and tell you how many primes you have up to a number is a little bizarre. If you want to write this more precisely mathematically, you could do this. Limit as x approaches infinity, p of x over log of x is equal to 1. And that's just crazy. All right. So this we understand. Um, twin primes we don't. Um, let's talk about a few other things. Let's talk about perfect numbers. So take a number like 10 and write down all of its factors, including 1, but not including itself. So what is 10 divisible by? 1, 2, 5. I think that's it. And if you add 1 plus 2 plus 5, you get 8. All right, which is less than 10. You had a question back in the set theory one to list all the factors of 24. And it has a lot of factors: 1, 2, 3, 4, 6, 8, and 12. And if you add those up, you get 20, 30, you get 36. So sometimes the sum of the factors is less than the number. Sometimes it's bigger than the number. Question is it ever equal to the number? Are there numbers where the sum of the factors less than the number itself is equal to the number? And we can get close. If you take a power of 2, the factors are all the powers of 2 less than that. When you add those up, you get the number -1. So that's pretty close. If you take a factorial like 24, you're definitely going to get something bigger. If you take a prime number, the only factor is 1. So that sum's equal to 1. So are there any numbers where the number is equal to the sum of its factors, less than the number?
Six.
6? 6 works, right? The factors of 6 are 1, 2, and 3, and 1 plus 2 plus 3 equals 6. So this is called a perfect number. Awesome. If the sum is less than the number, we call that a sad number. And if the sum is bigger than the number, we call that a happy number. You'll have a programming assignment in a few weeks related to this. So perfect numbers, the sum of the factors adds up to the number itself. 28 also turns out to be perfect. Its factors are 1, 2, 4, 7, and 14. And 14, 21, 25, 27, 28. And we know about a number of perfect numbers. And they're related to Mersenne primes. So anytime you have a Mersenne prime, you have a perfect number. And it's basically the prime number itself multiplied by 2 to this power -1. So take 3 and multiply by 2 to the first. Take 7, multiply by 2 squared. Take 31, multiply by 2 to the fourth. 31 times 16 gets you 496. Take 127, multiply by 2 to the sixth, which is 64. That gets you this perfect number. And we can prove that when you do this, when you take a Mersenne prime and multiply by 2 to its power -1, you get a perfect number. And since we're multiplying by a power of 2, all of these perfect numbers are even. So one of the unknown questions is, are there any odd perfect numbers? Don't know. It's an open question. All right, here's another open question. This is called Goldbach's conjecture. The conjecture says any even number bigger than or equal to 4 can be written as a sum of 2 primes. So for example, 4 equals 2 plus 2, 6 equals 3 plus 3, 8 equals 3 plus 5, 10 equals 3 plus 7, or 5 plus 5, 12 equals 5 plus 7, 14 equals 7 plus 7, or 3 plus 11, and so on. The claim is any even number can be written as a sum of 2 primes. And we don't know if that's true or not. It's something Goldbach noticed and claimed would probably always be true. He didn't have a proof. We don't have a proof. So it's an open question. So lots of open questions in number theory, especially around prime numbers and things related to prime numbers. All right, let me give you one more. This is sort of the quintessential number theory problem. So the Greeks knew this relationship about edges of a triangle. And if you have a triangle like this, x squared plus y squared equals z squared. And the Greeks, remember, were fascinated with whole numbers. So they were interested in knowing when you could make a triangle where all three sides were an integer number of units. For example, 3, 4, and 5. And it boils down to the question of when can I find integers that satisfy this relationship? 3 squared 9 plus 4 squared 16 equals 5 squared 25. Or 5, 12, 13. So there's lots of integer values x, y, z that satisfy this relationship. So being curious, they asked, well, what about with cubes? Are there positive integers that satisfy this relationship? And they were not able to find any. X squared plus y squared equals z squared. There's an infinite number of solutions to that. They could not find a single solution in positive integers that satisfied the cubic version. And eventually it was proven that there's no solution to this. There's no positive integers x, y, z such that x cubed plus y cubed equals z cubed. Now, if you let one of these be 0, it's pretty easy. Or if you use negative numbers, it's pretty easy, like 1 cubed plus minus 1 cubed equals 0 cubed. But for positive integers, no solution. And that was eventually proven. And so this raised sort of the general question about this type of equation. And so people studied particular versions of this. So anybody know what the name of this theorem is? If you watch a lot of sci-fi or Star Trek, you've probably come across it there at least.
Uh, three-body problem.
Um, Not exactly, although that's an awesome book and TV show. So there was a mathematician named Pierre Fermat, and Fermat was reading a Greek text on these kinds of equations. They're called Diophantine equations. He's flipping through this book and he comes across, the section that talks about this and talks about this. And he writes a little note in the margin to himself saying, like, this equation cannot be solved in integers. And more generally, this equation has no solution for any n bigger than or equal to 2. And he adds a note at the bottom of that saying, I've discovered a marvelous proof of this, which this margin is too small to write out. And after Fermat died, somebody found this textbook of his, and while flipping through it, found his note suggesting that he had a proof that there was no solution to this. But nobody ever found where he had written that proof down. And so this became known as Fermat's last theorem. And it was called a theorem because Fermat, who was highly respected, claimed to have proved it. And so people started trying to reproduce his proof. And for hundreds of years, nobody was able to do this. But lots of people came up with things they thought were proofs. And they would publish and say, here's a proof that this cannot be solved. And other people would look at it, and inevitably somebody would find a mistake. Some assumption they had made, something they had forgotten about, and the proof would fall apart. one famous proof of this relied on this fundamental theorem of arithmetic. And they assumed that that applied to all systems of numbers. And in the system of numbers they were using, somebody pointed out that it did not have that unique factorization. So this sat around for hundreds of years, and finally in the early 90s, um, a mathematician came up with a proof and published it. And as usual, somebody found a mistake in it, but he was able to fix that mistake, and he finally came up with a definitive proof that this can't be solved for n bigger than 2. And it was just one of those, really simple problem to write down. Anybody who knows how to multiply numbers can understand what you're trying to do here. You don't even need to know about fractions or decimals. It's just whole number multiplication. But for hundreds of years, it just baffled the best mathematicians of the time. And the proof that finally showed that this is not solvable is wild, insane, difficult. And it uses all kinds of machinery from largely an area called algebraic geometry and elliptic curve theory and all kinds of bizarre stuff that Fermat probably did not have access to. And he probably had a proof in his mind that made sense, but would have, fallen apart if he'd actually written it out and dug into it. But this is sort of the quintessential problem of number theory that again is like so easy to state, but frightfully difficult to prove, but was finally proven in the negative that there is no such solution. So that's kind of a smattering of some of the kinds of things that pop up in number theory, especially related to prime numbers, but not always. Just to kind of know what's out there. So Wednesday we'll go over the next homework assignment, and then we'll talk about something called the Euclidean algorithm and Bézout's theorem, which has to do with greatest common factors. We'll touch on something called the Chinese remainder theorem, and then we'll talk about a few applications of this. Probably finish that up on Wednesday, and then the next class we'll come back to doing propositional logic. All right, that does us for today. Have a good rest of the day, and I will see everybody next time. Take care.
Thank you.
You're welcome.